Hello students, this lesson is on logarithmic functions. Do your best to complete the table for the function below. F of x equals 2 raised to the x. Now this table gives us a y-coordinate of 8 and asks us to find the corresponding x-coordinate. So if I change the output to 8 and then ask myself what does x need to be so that this is a true statement, we see that x needs to be 3 because 2 cubed is 8. Similarly, if the output is 1, what does the x need to be? 2 raised to what power equals 1? And the answer here is 0. Now consider 3 as an output. 2 raised to what power equals 3? Well, this one is not as convenient to think about, and there is no easy answer here. But is there an answer at all? Well, look at the graph to the right here. This is a graph of y equals 2 raised to the x, where the x-axis is horizontal and the y-axis is vertical, as normal. By setting the output equal to 3, we are effectively trying to find the x-coordinate of this point. The graph suggests that there is an x-coordinate which will produce an output of 3, but currently it remains a mystery to us. We'll come back to this in a moment. A logarithm represents an exponent needed on a certain base to achieve a certain result. Consider the equivalent statements below. So here we have something that's known as exponential form. It's an exponential statement, b raised to the a equals c. b is known as the base, and as discussed in previous lessons on exponential functions, we want that base to be positive, but not 1. The a in this position is referred to as the exponent or power, and it can be any real number. And we'll call c the output of the exponential. It is the result of doing b raised to the a. And as a reminder, looking at the graph of y equals 2 to the x, the outputs of an exponential statement must always be positive. Now this symbol here in mathematics is a double implication. It means that the statement on the left and the statement on the right are considered logically equivalent. The statement here on the right is known as logarithmic form. The roles of a, b, and c are the exact same roles of a, b, and c in exponential form. So this b is referred to as the base of the logarithm, or the base of the log for short, and it also must be positive but not 1. C is called the argument, or the input of the log, and it must be a positive number because this value of c will be equal to this value of c in exponential form, which also must be positive. A is called the output of the log. It is an exponent. In fact, this number a will be equal to this number a over here in this context. Thus, a can be any real number. As far as language is concerned, in the case of the exponential form, we say b raised to the a is c. Or sometimes the word raised is left off, and you simply say b to the a is c. In log form, we would say a is log base b of c. Now let's try to make sense of this using a specific case. Complete the following statement and then put the statement in log form. 2 raised to the 3 is 8, because 2 times 2 times 2 is 8. In log form, we would say the following, that the exponent 3 is equal to log base 2 of 8. The exponent 3 goes in this position, the base 2 becomes the base of the log, and the output of the exponential 8 becomes the input or the argument of the log. If we didn't know that 3 was the answer, and you were asked to make sense of the expression log base 2 of 8, then the thought that should come to mind is log base 2 of 8 is the exponent needed on the base 2 in order to produce 8. So if you put a question mark here, you would say 2 raised to what power equals 8, and then try to answer this question. Of course, the answer to that question is 3. So log base 2 of 8 gives the exponent 3. Conceptually, log base b of c is equal to the exponent needed on b to produce the result c. So back up to our missing entry in our table. If we are trying to solve this statement, 3 equals 2 raised to the x. So currently this statement, 3 equals 2 to the x, is written in exponential form. I can isolate the x by simply rewriting this in log form. This x is in the position of a. So in log form, I will lead off with x is equal to. This 2 is in the position of b. So this will be a log base b, or log base 2. And then this 3 is in the position of the c, which is the argument of my log. So we have log base 2 of 3. And this logarithm, or log for short, represents this missing x-coordinate. So we have a notation, at least, for this missing x-coordinate, but how can I approximate its size? We can use technology to do this. In Desmos, for example, type in log, then hit the subscript button, base 2, then exit out of the subscript, and you can use parentheses to contain the argument, which is a good idea, and then put 3 into that position of the argument. And this gives us a decimal representation of this exponent that we are looking for. So it's about 1.585. Okay, let's go to the next page where we practice simplifying logarithms by identifying missing exponents. Simplify each logarithm by hand as much as possible. Use technology for the rest. Log base 7 of 1 is equal to something. Let's call it some variable, like a, for example, and then rewrite this log statement in exponential form. So the base is 7, we raise that to the a, and we want to produce a result that is a 1. That is the conceptual meaning of log base 7 of 1. It is the exponent needed on 7 to produce 1. And this tells me that a should be 0, because 0 is the exponent that you would place on a non-zero base in order to get 1 as the result. So we can say that this logarithm simplifies to 0. This next logarithm, log base 3 of 9. This represents the exponent needed on 3 to get 9. So you could put a question mark here and then say to yourself, 3 raised to what number would produce 9? And of course, that number would need to be 2. 3 squared is 9. So this logarithm simplifies to 2. Log base 4 of 4 represents the exponent needed on 4 to produce 4. So you can call this x and ask yourself, 4 raised to the x will equal 4. What does that exponent need to be? And the result needs to be a 1. So this logarithm is just 1. In fact, every time that the base of the log and the argument of the log are the same, that this logarithm will simplify to just 1. Also be careful that the base of the log you're writing as a subscript and slightly smaller, and the argument of the log is written the same font size as the log itself and at the same level. All right, this next one, log base 5 of 0.2 represents the exponent needed on 5 to get 0.2. So 5 raised to what power will equal 0.2? Well, it would be helpful to rewrite 0.2 as 1/5, and then we can identify that that power needs to be a negative 1. Because 5 raised to the negative 1 means 1 over 5 to the positive 1, which is just 1/5. On this next logarithm, we're doing 25 raised to what power will equal 1/5. Now I know that the square root of 25 will give me 5. So experimenting, if the power was 1/2, that would mean square root of 25. That would give me 5, but not 1/5. So if I want to do the reciprocal of this, then I need to use a negative power. So if I do a negative 1/2 power, this means to do 1/25 raised to the positive 1/2, which means do the square root of 1/25, and you can square root the numerator and denominator separately, so you get 1 over 5, which is, of course, 0.2. So the power needed on 25 to produce 0.2 is negative 1/2. Now for all of these, I'm going to change my notes to reflect the exponential forms of these log statements, and observe that all of these answers I've obtained are exponents. All right, moving to the next column. 3 raised to what power equals square root of 3? Well, the exponent needed to produce a square root is a 1/2 power. Therefore, this logarithm is 1/2. 0.5, which is 1/2, raised to what power will give me 1/16? Well, we need that power to be 4, because 1/2 times 1/2 times 1/2 times 1/2 is 1/16. So this logarithm simplifies to 4. 2 raised to the what power will give me 0. After thinking about this for a little bit, we recognize that there is no answer. Take a look at the graph of y equals 2 to the x. If I'm trying to solve 0 equals 2 to the x, then that's equivalent to trying to find a point on this graph where the y-coordinate is 0. But this graph never intersects the x-axis or goes below it. The result of an exponential must be a positive number, not 0 and not negative. This is what we meant when I said C, the output of an exponential, must be strictly positive. Thus, this situation is not possible, and we would say D and E for the result of this logarithm. The next one, 2 raised to what power, will equal negative 3. Well, this one is also not possible because the output of an exponential statement must be positive. It cannot be 0 or negative. So again, this logarithm does not exist. And this last one, 2 raised to what power equals 3. This is a case where the simplification will not be a convenient number. However, this is possible. So we reach for the calculator, as we did before, and we get about 1.585. And this is a rounded decimal version. It turns out that the answer here is irrational, meaning the decimals go forever without a repeated pattern. So the best I can do here is give a rounded version of it. Now there are 2 logarithms with bases that use special notation. One is called the common log. It's a log that looks like it has no visible base. But when you see log without a visible base, the default is always a base 10. So log of a, or log base 10 of a, represents the power needed on 10 to produce a. So for this first case, pencil in the base, and we are trying to solve 10 raised to the what will equal 1,000. And the answer to this is 3. So this logarithm simplifies to 3. On the next one, Again, there's a base 10 implied. So 10 raised to what power will equal 0.1. Keep in mind that 0.1 is 1/10, at which point we can recognize that the power needed is a -1 power. So this logarithm is -1. And the third one, again, base 10 is implied. 10 raised to what power will produce 3. And this is a case, again, where we will not have a convenient answer. So the best I can do with this is to reach for the calculator and get a decimal approximation. And we type log. I recommend you put the arguments in parentheses of 3. And if I don't specify a base, the technology assumes the base is 10 and gives me an appropriate answer. It's about 0.477. I can also put the base in there explicitly, log base 10 of 3, and it confirms the same answer, which is about 0.477. Now there's a second special logarithm called a natural log. It's written ln of a. And a natural log is simply a logarithm whose base is the irrational number e, called Euler's constant, where e is about 2.718. To see it with more precision, simply type in lowercase e into Desmos, and it gives you a more precise but rounded version of e. E is also an irrational number, meaning the decimals go forever without a repeating pattern. So ln, or natural log, of e, when you see the ln, there's an implied base of e. So this logarithm represents the exponent needed on e to produce e. So in other words, we are trying to solve e raised to what power will equal e again. And of course, the solution to this is that e to the first power will equal e. So this natural log of e simplifies to just 1. The base e does not need to be written. I'll erase it. Same thing over here with these logs without a base. You do not need to write the base 10s, so I can erase them all. Now the next one, natural log of 1. Imagine a base e being there. E raised to what power will equal the argument, which is 1. This does have a convenient answer, that answer being 0. Remember, any non-zero number raised to the 0 will simplify to 1. So in summary, the natural log of 1 is simply 0. And the natural log of 3 means we're trying to find e raised to some power, and we want to get 3 back. Well, this is a case where the answer is not an obvious, simple number, and we need to use technology to do this. So if you type in ln, and then parentheses for the argument, and put 3, we get a decimal of about 1.099. You can also get the same result by typing log base, put an e there, and then as your argument put 3 again, confirming the same result. So natural log of something is the same thing as log base e of that thing. And so we get approximately 1.099 using technology. Okay, going on to the next page. Logarithms give us the notation to describe the inverse of an exponential function. So let's consider this function. F of x equals 2 raised to the x, or you could write y equals 2 to the x. And let's fill in this portion of the table. When x is -2, the y-coordinate will be 2 raised to the -2. The negative power means we do the reciprocal of the base and raise that to the positive power. That gives me 1/4, which gives me this point in our graph. When x is -1, this means do 1/2 raised to the 1, which is just 1/2, giving me this point in our graph. When x is 1/2, we have 2 raised to the 1/2 as the output, which is radical 2, which is about 1.4, giving me a point roughly right there. When the input is 1, the output will be 2. And we could do some more points. When the input is 0, the output is 1. When the input is 2, the output is 4, etc. And we have a growing exponential function. Only positive outputs were possible. Everything in this right-hand column should be a positive number, not negative, not 0. Now to go backwards in the table, it is handy to have an inverse function. The process for finding an inverse function is to take this equation and solve it for x. Well, the way to do that is simply to convert this to log form, which would give me the exponent x is equal to log base. The base will be 2, the same thing as the base of the exponential form, and then the argument here will be y. Then we switch to our inverse notation, so f inverse of y is equal to log base 2 of y. This is the function I would use to reverse my table and input y's to produce x's. Change y to 4, and the x-coordinate will be log base 2 of 4. This happens to be a convenient number because 2 raised to what power equals 4, and that exponent is simply 2, confirming that 2, 4 is a point on this graph. Now in some cases, this log notation isn't very necessary. For example, trying to reverse this one, I'm really just trying to say 2 raised to what will produce a 1, and the answer to this is 0. Of course, I can arrive at that 0 by saying that the answer is also log base 2 of 1, and then reason my way through this to conclude that this must be 0, or reach for a calculator and confirm that this is 0. In this next case is where the log notation becomes crucial, because the x we need is log base 2 of 3, which does not simplify to a convenient number. From previous slides, it was about 1.585. And then this last one, similarly, log base 2 of 0.8 is the expression I'm looking for. If you reach for a calculator, this will be about negative 0.322. So the inverse function helps me go from y to x, whereas the original function helps me go from x to y. Now I'm going to do something I don't normally recommend, and is I'm going to rewrite the inverse function in terms of x by simply changing the input variable back to x. So this would read f inverse of x is equal to log base 2 of x. Furthermore, if I assume the output of this is now a y-coordinate, I get this statement, y equals log base 2 of x, which is the same thing as this statement here, but the x and y have been switched. This gives me a new class of function that I can talk about graphing, where the x-axis is the horizontal axis and the y-axis is the vertical axis. So this orange graph that's already here is the graph of y equals 2 to the x, which is this function, which is logically equivalent to this equation, x equals log base 2 of y. So if you type in any of these equations into Desmos, it'll produce this graph. So to make the green equation, we take this orange equation and switch the x and y coordinates. That's going to produce an interesting effect when I try to graph the green equation. Every single point on this orange graph over here has an x and a y coordinate, which are going to be reversed to make the green graph. So this point 2, 4, switch the x and y coordinates to be 4, 2. This point 1, 2 becomes the point 2, 1. The point 1 half comma radical 2 will become radical 2 comma 1 half. 0, 1 becomes 1, 0. Negative 1, 1 half becomes 1 half negative 1. Negative 2, 1 fourth becomes 1 fourth negative 2. If I were to do this with more points, we would see the following function. This is a graph of y equals log base 2 of x, or you can also say x equals 2 to the y. Visually, the green result is symmetric with the orange graph with respect to this diagonal line y equals x. And this is because the roles of x and y have been reversed. Further, notice that the domain and range of the orange graph, the domain is all real numbers, and the range is the y-coordinates must be positive only. Well, when you switch the x and y coordinates and regraph, the domain and range switch. So it's now the domain that is positive numbers only, and the range that is all real numbers. You can see that visually from the green graph. This green graph only contains points where the x-coordinate is positive, but where the y-coordinate can be any real number. Let's confirm this with technology. Here's a graph of y equals 2 to the x. If I do nothing more than simply put this in log form, it would read x equals log base 2 of y, which is the same graph as the blue graph. But if I now switch the x and y coordinates, then we take the blue graph and make the switch. So x equals 2 raised to the y, we get this purple graph. And the purple and green graphs are symmetric about the line y equals x. Or another way to write the purple function is to write it in log form by saying y equals log base 2 of x. That gives me the red curve, which is the same thing as the purple curve. So each curve has two different ways to write its equation. So the blue and the green produce equivalent graphs, because all I've done to go from blue to green is convert from exponential form to log form. I have not yet done a switch of variable. But once I switch the variables as well from either of the first two forms, then I get the purple and red graphs, which are equivalent to each other, because the purple is written in exponential form, and red is the same relationship between x and y, but written in log form. Okay, let's go to the next page. Find the inverse of each exponential function below. On each grid, graph both the function and its inverse function using x as the input variable. If you begin with an exponential function y equals b to the x, then solve for x, then switch the variables, then put in exponential form. Now these first two are equivalent to each other and produce the same graph, and these second two are equivalent to each other and produce the same graph. So if you're given a function in this form, y equals b to the x, then its inverse function with x as the input variable will be this one, log base b of x. So here in the case of g equals 10 to the x, g inverse will be equal to log base 10 of x, or you can just write log of x. Now if you graph 10 to the x first, it goes through 0, 1, and 110, and 110 is off of our scale. But if you take this graph and reflect it around the line y equals x, you will get a graph of y equals log x. If h is equal to e to the x, then h inverse of x will be log base e of x, which we will write as ln, or natural log of x. Now h will pass through 0, 1, and 1e, and is also a growing exponential function. So 2 points that the natural log of x will pass through will be 1, 0 and e1. And in this third case, if k is equal to 1/2 to the x, then k inverse will be log base 1/2 of x. 1/2 to the x goes through -1, 2, 0, 1, and 1, 1/2, among other points. It is a decaying exponential. And if you reflect this one across the line y equals x, you will get a graph that contains the points 2, -1, 1, 0, 1/2, 1, follows the y-axis up, and then goes off into the fourth quadrant. The red and black graphs will intersect on that line of symmetry, y equals x. Now use technology to graph several examples of y equals log base b of x for various choices of a positive base. Then complete the following statements. So type in y equals log base b of x, then add a slider for the base. Let's put 0 as a lower limit and 2 as an upper limit. Step size 0.01. Change our animation mode and hit play. So when the base is between 0 and 1, you see decreasing functions. When the base is more than 1, you see increasing functions. I will also graph the green exponential curve, y equals b to the x, and the orange line of symmetry, y equals x. I'll drag b to 0 and then hit play and focus on the symmetry of the red and the green graphs across the line y equals x. The green graph is an exponential function as a function of x, and the red graph is a logarithmic function as a function of x, both with base b. Now showing only the logarithmic function. As the base varies, notice a few things. The graphs only exist in the first and fourth quadrants. The argument of a log, which is x in this case, cannot be 0 and cannot be negative. Also notice that all the graphs pass through the point 1, 0. Furthermore, if I park b at 2, a second point will be 2, 1. Change b to 3, and notice that we now go through 3, 1. Change b to 4, and we go through 4, 1. And you can see a pattern. Change b to e, and our graph goes through e1. Now when the base was more than 1, the function is increasing. And if b was between 0 and 1, the function is decreasing. In either case, the domain is x has to be positive. Keep in mind that x is in this position when looking at this function. That is, the argument of a logarithm must be positive. And the range is y can be any real number. In all cases of a defined logarithmic function, all y coordinates are possible. In fact, looking at the graph of e to the x here, it's tempting to say that there might be a horizontal asymptote, some sort of horizontal line that the graph never goes higher than. But let's put a horizontal line in here, such as y equals 10, change my vertical scale so I can see it, and it's tempting to say that this red graph will never go higher than that blue line. But if I change the scale of the x-axis, eventually you will see the logarithmic graph go higher than that height. In fact, from this point of intersection, we can see that it required an x-coordinate of more than 22,000 in order to get that y-coordinate of 10. Now, no matter how high of a y-coordinate you pick, if you go far enough out to the right, the red graph will go higher than it. So this is why the range is going to be all real numbers. This red graph will attain all heights. Okay, let's go to the next page. Use transformations to graph the following function. Give its domain and range. Our parent function here is log base 3 of x. A few key points will be, if x is 1, then y will be log base 3 of 1, which is 0, because 0 is the power you put on 3 to get 1. If x is 3, matching the base, then log base 3 of 3 will be 1, because 1 is the power you put on 3 to get 3. So 2 key points on this will be 1, 0 and 3, 1. If you are struggling still with evaluating log functions, then one strategy will be to convert this to its exponential statement, which would read 3 raised to the y is equal to x, and then make your table of points backwards. Pick some easy y coordinates like 0 and 1, and plug them in to this statement. So if y is 0, 3 to the 0 will be 1. And if y is 1, 3 to the 1 will be 3, confirming the 2 data points. Now the rest of this graph will be a function that follows the y-axis down and then arches over into the first quadrant. Now if you look at this argument, there is both a reflection around the y-axis and a horizontal shift occurring. The coefficient of x is not 1, it's currently -1. So I do recommend that before you go much further, you rewrite this argument, factor out that negative, and writing it this way. The next transformation I should do is log base 3 of negative x. This will be a reflection of the orange graph across the y-axis. And I'll keep track of the 2 key points as I do these transformations. Next, I'm going to replace x with x minus 2. This is a shift right 2 units. So the green graph has the y-axis as a vertical asymptote, and we're going to shift all of this right 2 units, creating this blue graph with vertical asymptote at x equals 2. Now as our final transformation, we will add 1, which will shift the blue graph up 1 unit, giving us this black graph as our final answer. Visually, we can see that the domain of the black graph is that x must be strictly less than 2, and the range of the black graph will be all real numbers. The black graph, even though it flattens out, will go up forever and will also go down forever with the asymptote. We can also calculate the domain by grabbing the argument and saying that the argument must be positive, which means that negative x plus 2 must be positive, and if I add x to the other side, the x must be less than 2, confirming what we see in the visual. Okay, this concludes our lesson on logarithmic functions.